Okay, I think it's already half an hour past. So, okay, so welcome everybody to this discussion session, which will be animated by Thibault Damour, Ashoke and Andy Strominger. So I think we should try to have a general discussion on BMS, soft theorems, their relations, and somehow the relevance of all this for the general theme of the workshop, namely for the two-body problem in GR. So we thought that, I don't know if our three speakers could perhaps spend, say, 10 minutes or so to say which are, in their opinion, the most interesting things to discuss, to understand what are the challenges and so on. And then, that could be a good starting point for a general discussion. Then, of course, everybody is welcome to intervene, ask any sort of questions. So I don't know if we have to go by alphabetic order or as you prefer. Perhaps Thibault, you want to start?
Okay, I will be short because I found quite interesting everything I listened to, and I listened to everything, I think. But I got also quite confused finally. And at the end, like Gabriele, I would like to ask the simple question, because beyond this compatibility between, if you have a solution of Einstein equations, there are terms in the metric which are non-local and which encode information about many nonlinear effects that have happened and things like that. And they are encoded in those balance laws. But from the practical point of view, when there is a two-body scattering, either classical or quantum, with initial momenta, final momenta, I mean, for the hard bodies, let's say, two black holes, and then they emit radiation. So those super translation balance laws, what do they give us as precise conservation law, if any, that we can apply to learn something about the scattering and the effect of radiation reaction? Finally, I'm confused about this.
Mm-hmm.
In the case of massive scattering of massive bodies, because I also think there is a big difference in the idea whether BMS is a symmetry or not. If we are talking about purely massless scattering, like pure gravity, or the scattering of massive bodies emitting essentially soft radiation. So is there an answer to this question?
Okay, so this is a very nice point, but perhaps we should have
Yes.
also the other panelists say something, and then we try to put everything together. I may also have a few questions myself, but please. Ashok, perhaps?
Okay, I can go ahead. So maybe I'll raise two questions. Okay, one of which I already raised, in fact, during my talk, and some discussions were there, but maybe I should emphasize it again. Okay. And which is in this classical scattering process, what we had found is that if you look at the late time fall off of the gravitational waveform, then certain terms somehow do not depend on the final state massless particles. And it seemed very strange because in our calculation, at least it came out after some analysis. Okay, but if it's true, it must have a better understanding. Okay. And as an example, I can also mention, in fact, one of Gabriele and your collaborators' paper, that if you take, for example, the massive two particle scattering, massless two particle scattering, right? Which you have studied in detail. Okay. What this result tells us is that if we look at the term proportional to log omega or omega log omega square, then it doesn't matter if the particles scatter or just go straight, okay? Because it doesn't depend on the final state massless particle momenta. So whether the particle went just large impact parameters, say just went straight, or whether they have a small impact parameter and they bent, you'll get exactly the same coefficient of those terms. And this seems a puzzle, that why should it be the case? And it must have a better understanding. So that's one thing I would like to understand.
Okay.
The other question I raised is about in quantum soft theorem. Okay. I mean, we know that BMS, for example, gives the leading term in the classical soft theorem very well. That's the memory term. Okay, and there are quantum versions of this, which is the Weinberg soft gravity theorem. But at subleading order, we have logarithmic corrections. And those seem to be somewhat harder to understand from the perspective of asymptotic symmetries. I know that Alok and Miguel has written some papers on this. So I was hoping that one of them will be around and can maybe explain to us what it is about. But that's something I'd like to understand better. I think these are the two questions I'd like to raise at this stage.
Okay, maybe listen also to Andy.
Yeah, so from my point of view, this workshop is, covering sort of one really important side of a much bigger thing that I've been thinking about. I mean, a lot of my career, I was, thinking about quantum gravity and short distances and string theory and so on. And it's kind of like we were all on this sort of march into the ultraviolet, and then we looked behind us and all the interesting stuff was way back in the infrared. Yet the stuff that we had been doing, trying to understand, I think our modern understanding of BMS wouldn't have be at the state that it was if we hadn't explored different kind of mathematical ideas in string theory. And so that's sort of a sort of wonderful example of the unity of different parts of physics. But also, it's so wonderful now that it seems to be, and very exciting to me, which I think is the sort of the focus of this workshop, that it's actually connecting to experiment. And it is really amazing. I mean, I think it should make all physicists feel good that no matter what you do, you have to wrestle with facts, and those facts just have a tendency to push you in an interesting direction. And I was kind of amazed. One of the things that I said in my talk last week is that there is no definition of the scattering problem in general relativity. And the first part of that is the leading order fixing the super translation frame at infinity. And so it was interesting to see the numerical relativist, this beautiful talk this morning, trying to compare with their numerical analysis with experiment, or struggling directly with how to fix the BMS frame. And I have found also that, ideas in quantum gravity, so we're not going to I'm not one of those people who thinks we're going to do an experiment that will tell us about C strings or something like that. Nevertheless, I found both in interacting, like what the focus of this workshop, theorists thinking about basic concepts of theory and interacting with people trying to do experiment, it forces you to think about things in a new way. and often leads to, and this also happened to be in my interactions with the Event Horizon Telescope, it leads to interesting new things in fundamental theories. So I think it's all sort of a very exciting and wonderful development. Now, as far as what Thibault said, I think that the question you're asking, I think it has a very definite answer. At leading order, as far as the leading large diffeomorphism. The subleading, it gets more complicated. And Ashoke was asking a question about the subleading stuff. The leading order, there's no corrections, the theorems are exact and so on. The subleading stuff, and I don't know the answer to Ashoke's question. I've been asking it myself. I think I asked it. I think maybe I asked you during your talk, but it's certainly a really important question, which and also it was I guess also there was some question about how that is going to show up in the experiments, which I think also focuses our thinking about it in a really nice way. I mean, BMS didn't have, that was a long time ago, there was no thought of experiments. So I think a lot of their confusion, and they were confused about very many things, was because they didn't have this kind of interaction. Okay, that's my.
Okay, but if I can rephrase Thibault's question, what do you think super translations and BMS adds, say, just to the leading soft theorem? I mean, suppose I didn't know about BMS, but I knew about Weinberg's soft theorem. What am I missing from my description of the gravitational scattering problem? I don't know if this is a good rephrasing of what Thibault was asking.
In part, yes.
Well, sorry.
So even memory, I think.
Soft theorem, yeah. I mean,
I think in your talk, you connected directly memory to soft theorems as well, right? Without going through BMS.
There are Fourier transforms, right?
That's right. The Fourier
transform
nice.
of a pole is a theta function.
Yeah, exactly.
And Brzezinski and Thorne had a theta function, and Weinberg had a pole, and
right.
Yeah, they computed it. I mean, it's exactly the same formula with all the same 2 pi's and everything. Just one is in momentum space and one is in position space, because one was a particle theorist and the other was the others were relativists.
But of course we know that, but this is not, the full story we want to learn from a gravitational scattering experiment, where you want to really measure what comes out. What comes out is not just Weinberg in terms of radiation. You want, for instance, to calculate the amount of energy which is radiated, and I don't think the Weinberg approximation is good enough to compute the total radiated energy.
No, but you see, Weinberg was a little more than BMS.
Right.
So BMS didn't have any conservation laws. Mm-hmm. And they had symmetries of the symplectic form at scri plus and scri minus, but they didn't understand how the BMS frames were matched in the past and the future. So they wouldn't have been able to, it just wasn't a thing that they were thinking about.
Yeah.
And there was a lot of discussions on restricting the phase space of GR in a way that would kill the symmetry. But there was never a well, actually, people did think about it. At least I know that Abe thought about, could you match the BMS frames? And they thought about it and concluded it was impossible. But that was because they were confused about the peeling theorem and all that stuff, which Thibault was mentioning the other day. That this was at a much earlier phrase that they were trying to think about. So, but Weinberg implicitly knew, his theorem implicitly knows about the antipodal matching. So that tells us that we do have an infinite number of conservation laws in general relativity related to the leading soft theorem. And those are exact classical and quantum conservation law. There's a number you can associate. There are an infinite number of numbers. For every spherical harmonic, there is a number you can associate with the incoming data that is equal to a number you can associate with the outgoing data. That's a conservation law, not just energy and momentum. How exactly you think about it, it's subleading orders. Some things are clear, other things are, there's more to be understood, as Ashoke points out.
But these conservation laws, they involve the boundary mass aspect. So it's a consistency condition of having solved Einstein equation and having the theta phi dependence of boundary mass aspect satisfying Einstein equation related to hard energy emission.
Well, so are energy and momentum conservation a consequence of the Einstein equation?
Yes. But
it's all a consequence of the Einstein equation.
I understand. It's just some of them are more directly useful for the scattering problem.
Well, I mean, some of them, well, but I mean, the ones that you need for the memory are, I mean, those are useful. They predict the memory. And indeed, there's even subleading ones that we understand well enough. The subleading ones we understand well enough. There's some things about them we don't understand, but we understand them well enough that we can, there's new memory effects, the spin memory, which is concrete enough that are the numerical people, there's, prediction. Maybe won't be measured very soon, possibly at LISA. But so yeah, they have real consequences. The fact that GR in asymptotically flat space-time, the phase space of it includes, the phase space of general relativity is not just given by the, you can't characterize it by just the coordinate invariant, by the Newman, by the, coefficients of the Weil tensor on SCRA. You need the, what we refer to as the BMS frame, and its subleading order. There's another frame associated with the angular momentum aspect. And that is also leading to some measurable predictions. Of course, everything is, so in the BMS frame, so you could just take, if you took some, I guess it's a question of how you would, if you have some maximal evolution of the Weil tensor computed on some series of space-like slices, you still have to attach the hats on the top of the bottom, which are scribe plus and scribe minus. And there has to be a rule for doing that. And the rule for, I mean, obviously, if there were no rule for doing that, you could attach scry minus, and then you could boost scry plus before attaching it, and you could have a Schwarzschild solution or just a single massive particle that came in with one energy momentum and went out with another one. If you don't coordinate the way you, now, of course, we all understand for the Lorentz group exactly how to deal with that ambiguity, but there's a much more subtle version of it that, you know, there's a parameter of how you attach at every point on the sphere. And, you know, that what we want to do, and the only sensible proposal that I've seen is the antipodal matching of the Bondi of the Bondi mass aspect, and also the super translation, the CZZ, as somebody was calling it. Now, if you solve the Einstein equations, but there's more at subleading orders. So if you solve the Einstein equations perturbatively, you see, if you solve the constraint equations on scry, they give you their equation for the U derivative of the Bondi mass aspect. They don't fix the U independent part of it. That's where you need the matching. Right. So if you only had the news on scry, you wouldn't be able to reproduce the geometry. You need an initial condition for the Bondi mass aspect coming from scry minus. Now, if you then expand the Einstein equations in 1 over R around scry, the constraint equations, the equations of motion, determine the metric, but at every order in 1 over R, there's an integration constant. So there's an integration constant for the angular momentum aspect. Okay, so so that has to be specified. Yes. How you fix those. Yes, Thibault.
Yes, I fully understand, but you see, I come from the other side. We invented, I mean, knowing that Bondi was totally, I mean, was away from the source, could not connect to the source. We developed the multipolar post-Minkowskian, which is just a perturbative thing, but which is connected to the matter. And we got all the memories, I mean, before Christodoulou actually, and all that connected with the source. And in this framework, it seems the Poincaré group is a good symmetry, but it's not clear that there is an additional symmetry linked to, because you are always connected. You are always uniquely connected to the source. You never have, you know, 1 over R. You compute the 1 over R expansions from something in the bulk.
But
so I would be interested in understanding how the super translation conservation balance laws add something more to solving explicitly Einstein equations. Let's say they are solved perturbatively, both in the bulk and connected to both scry minus and scry plus.
Are you talking about solving the Einstein equations on a series of space-like slices?
No, no.
Or you want to impose data on scry minus and evolve it to scry plus?
Neither. Okay, the multipolar post-Minkowskian thing is, it can be applied to the scattering problem or more generally to binary systems or whatever. You have a combination of approximation methods that can solve Einstein equations everywhere, in the near zone, in the wave zone, connected for post-Minkowskian scattering. And you are always connected between the system and infinity. And then you find in some cases that scry is okay, in other cases that scry, the peeling is wrong, for instance, or whatever. Mm-hmm. So that's why I'm really interested in understanding where the super translation ambiguity would arise here.
I may have a comment on this, but I have seen that Geoffrey has been raising his hand for a while. So
yeah, I can just
why don't we listen to Geoffrey first?
Thank you. So because we had some work with Ali and Roberto, and also with Guillaume Fay and
Luc
Blanchet. So on exactly that problem. So trying to exactly relate the Bondi angular momentum aspect and the Bondi mass with the source. And indeed, that's required to be able to understand these conservation laws in terms of scattering and what do they say about the source. So here we'd like to give you the point of view, a point of view that you have the Peters Matthew. Peters and Matthew showed how you can use the flux balance law of energy and angular momentum to understand the equation of motion of the binary problem of you understand then the secular change of the major axis and the eccentricity of your binary system from the flux balance law of the energy and angular momentum. After you relate the quantities at infinity, the radiation in terms of the source parameters. So now if you have a scattering problem with now additional parameters like n-body, so the Bondi mass aspect already will contain information about the individual velocities and masses of the individual bodies. So already at leading order for the Bondi supermomentum law, it should give you constraints on the source parameters of and you need more than 2 laws because you will have more source parameters than just two quantities. So it looks to me like immediate that all these conservation laws will contain non-trivial information about the source parameters.
Oh, I would disagree. I think you have explicitly connected, yes, the Bondi mass, but it shows that all the information was there already before. It's a way to go to the Bondi gauge from the description, but you don't learn anything new.
But what about the Peters and Matthew example?
Yeah, but that's okay. This is the ordinary. That's what we use all the time. Yeah, like in the recent work linked with Gabriele, I mean, we need to have angular momentum loss in post-Minkowskian now to connect scattering and gravitational reaction corrections to scattering. Okay. Yeah, I would be very happy to be able to have more. Okay, more balanced laws directly useful. It's just I don't see.
Yeah, in this connection, may I mention some work I did long ago with Wilkowski and others, which refers precisely to the massless scattering problem. So there we assume we have 2 incoming massless particles, so something at sky minus. And then we compute the scattering amplitude to leading order in G Newton. So this is a leading iconal approximation, if you want, by computing the Bondi mass aspect, actually the Bondi masses directly integrated over the angles at sky plus and sky minus. And because the 2 particles, as they hit each other, undergo some time shift, some Shapiro time delay, you find that you can reproduce this way the leading iconal formula, which is known in many other ways. For instance, what Toft did in '87. So I wonder, okay, how that calculation matches with what Andy was saying about the conservation of the Bondi mass aspect at sky plus and sky minus, because somehow, I see some kind of clash. I mean, in other words, it was very important for us that the arrival time retarded time at sky plus, was different from the on the advanced time at sky minus of the two particles. And it was precisely this time shift which gave the S matrix. So I hope Andy is not saying that that S matrix has to be trivial. Yes.
Well, I think maybe I would address both at the same time.
The two particles, I mean, somehow we had to solve the theory in the bulk when the two particles cross each other at some impact parameter B, you know, the two shock waves produce time shifts in the trajectories, and you read those time shifts at sky plus, and we had a formula for the S matrix in terms of Bondi masses at sky minus and Bondi masses at sky plus. So it looks very much like things you are saying, except that it's not at all trivial. I mean, somehow we got finally the right iconal formula.
Yeah, so first of all, let me agree with Thibault. There is in fact nothing new under the sun since Einstein. We could have written down the Einstein equation, we would take the initial data, get a giant computer, evolve it, there's nothing more to say. And if we can put in our experimental devices, we can predict what they will see. We never need to talk about large gauge, we don't even need the conservation because the Einstein equation already knows about the conservation law. However, it sometimes happens that our computers aren't big enough and analytic methods are useful and they tell you where to look for interesting physical phenomena to measure. And moreover, we often get things wrong if we don't understand these subtle conceptual symmetries. And I think that's exactly the situation we're in. I don't think there's anything wrong with the way that the calculations were doing before, but it's really interesting that just today, two examples have come up, both from numerical and the thing that Gabriella makes up. So yeah, they did this. We heard about it in that talk this morning. They put it on the computer and they didn't see the memory. They got the wrong answer. And they got the wrong answer because of they realized they got the wrong answer, and because of this understanding of this BMS frame at infinity, they were able to go back and correct their computer code and adjust this error. They predicted the wrong waveform. It goes back, it doesn't go back. And that's because
Yes, but PN had predicted the good memory before. Yes.
Yes, okay, but it doesn't always. I know you knew about this, Thibault, but I don't think you knew about the subleading memory. And so whether you could have implicitly known about it in the equations, but they're interesting things. No. Now, Gabrielle has mentioned yet another example. Okay, so at Tufts had this S matrix that where he had this shift, things coming in, things going out. Now, his shift did not have the antipodal, was an antipodal shift. It was a non-antipodal shift. He's gone back and corrected it. Okay.
Now, yes.
20 years later, after the stuff about BMS came out, he's corrected it and he's got somehow now it's antipodal. I don't understand it. Okay. Yeah, just last night, I was reading Polchinski's paper about this, which also does not have it. Chaos of the black hole aspect also does not have this antipodal shift. At Tufts, Polchinski, none of these people were careful about what the BMS frame is, right? They didn't. Yeah, so, I don't know. I don't understand Polchinski's calculation. I think that, the whole effect is a coordinate transformation, but he doesn't specify how he's matching his past and future BMS frame, as with a Tufts. I don't know if these calculations are right. These people don't really make mistakes, but I want to understand it.
I
don't know. Sorry, Gabriel, but I don't know what your rule was for matching the BMS frame, and I don't know what my rule would be in that calculation. So I think that both whether you're doing numerical or pure theory, I'm sure that Thibault got the memory effect right the way he was doing it, but I think when, you know, however you do the calculation, even though, you know, Einstein said it all, there are still things that we need to understand. And on top of that, as a third point, they're conceptually interesting and they're fun. And I also think that there are these symmetries, these infinitely many symmetries that are controlling gravitational scattering. And I think they will be very important in understanding the structure. I think that they should have a quantum analog of some kind, which we don't understand. And I think they will be very important in understanding what quantum gravity is. So, you know, I think—
Would you say, the symmetries, when you say gravitational scattering,
yeah,
mean always massless scattering? No, massless.
No. It fully goes to the massless case. We had a beautiful talk about that from Miguel.
Yes, I understand. But to me, it looked more intuitive that there could be really this full BMS symmetry for the massless case in the limit of massless, ACV, Amati, Ciafaloni, Veneziano, but not maybe in the massive case.
No, it's a match. No, it completely covers the massive case. Then that's very important. I mean, the soft theorems involve massive particles. It started out with massive.
I know. Yeah. I'm talking about the symmetry here.
But the soft theorem is the symmetry. The soft theorem is the word identity of the symmetry, and you can work back from the soft theorem to rewrite it as a symmetry.
But I mean, also for the soft theorem, you don't really need the BMS. You can do with the gauge invariance in much simpler way. So why are you stressing BMS for the soft theorem?
The field theorists would say, who needs BMS? And the GR people would say, who needs soft theorems? And the memory people would say, I don't care about either of them. But when you put everything together, you learn new things, right? I think that there's power in uniting things which are obvious from one point of view can be obscure from the other, and having measurements that we can at least imagine doing. It's really nice. You know, it was a little hard with string theory, you know, thinking about measurements that you weren't going to do in the next century, you know. But it's nice to have, in this subject, it's nice to have measurements, even if they're not going to be done in the next 5 years. You know, it's quite possible that we'll have all kinds of, you know, with Lisa, that we'll have all kinds of measurements of maybe even subleading memory effects. So you can learn new things. So there have been a plethora of new soft theorems that could have been discovered, you know, 50 years ago, that were suggested by asymptotic symmetries. There have been new asymptotic symmetries that have been found from the soft theorem. There have been new memory effects. There have been also, this story started in gravity, and it's going into Yang-Mills theory and into QED. People have been looking at proposals for, you know, memory in Billion gauge theory. The electron ion collider that's building is going to try to measure color memory. So, you know, when you put together different things, the whole is more than the sum of the parts. And I haven't mentioned trying to, one of the things that's really driving the field now, but this conversation is trying to understand how to generalize ADS-CFT holography to flat space. For that, you need to know what the symmetries of flat space are. That is the starting point. And we don't know, the starting point of ADS-CFT was the symmetries matching between the two sides of the equation. And we don't know the symmetries of quantum gravity and flat space. And we know we do know that they're incredibly rich. And the leading memory effect is certainly one of them. So yes, if you just want to do one thing, you can consistently do the one thing. But if you can relate different people working on different things, everybody learns more. That's, I don't care. Sorry for, I should mute myself before.
There is a question by Ali. Ali?
Hi, yes, thank you. So this is a comment and also a question for Professor Damour. So Ashoke in some of his papers mentions that, I mean, these Bondi equations for the mass and angular momentum aspects are exact equations. So, but the post-Newtonian formalism, if I'm not mistaken, breaks down in the merger phase on when the problem is very highly strong gravity. So so I agree that we can read off memory terms and all that in the post-Newtonian framework, and I realized this when I was working on these papers with Geoffrey. But would you agree that in the merger phase, this is an advantage for the Bondi equations over the post-Newtonian, because I mean, the post-Newtonian breaks down?
Yeah, by the way, yes, but only in part, because as you know, the effective one body has predicted the merger and the full waveform, so it goes beyond post-Newton, or maybe you don't know. But anyway, perturbation theory can be improved compared to usual PN and predict the full signal. The problem of the Bondi equation, let's say, evidently everybody wants to put together exact equations. The problems, for instance, is when you write the news, you don't connect in Bondi the news directly to the source. Okay, so it's useful to have a formalism which says that the news contains the tail, and the news can be expressed in perturbation theory as a direct hereditary functional of the motion of your bodies. Okay, so you need to patch everything together, and we are lucky that even the merger of two black holes is quite describable by perturbation theory up to merger and beyond merger. So, but evidently we want to have all the tools together.
Right, and just another minor comment, which is that you can view this Bondi equation, for example, for the mass aspect, as a perturbative equation. For example, you put in the flux term, you consider just the leading effect, and then from the equation you read off the linear term, I mean the memory term, which is like a higher effect. I mean, you can somehow iteratively, so I mean, you can view this equation as an iteration to obtain higher order PN terms in terms of the lower ones. But I agree that I don't get something that you didn't have in your results, but I mean, this is also a viewpoint.
No, we need to put together all the information we have.
Yeah, thank you.
Could I ask a follow-up to Thibault on that? So I understand that, well, I sort of understand that the methods that you're using can be, do the whole merger. But why does that work? I mean, usually if you, I mean, certainly GM is becoming of order 1. And often in physics, when the expansion parameter is no longer small, sometimes you can resum perturbation theory to get it at part of it, but there can be non-perturbative effects that don't have any sign. So why does it work so well?
It works. I think the basic reason is that the power, the emitted gravitational wave power you know, in units where G, C5 over G, in Dyson units, Freeman-Dyson, becomes dimensionless. And in these units, that you say the power of emission of gravitational waves at the moment of merger, at the highest power, is equal to 10⁻3. So it's a small number. That's
why does it end up being so small? Is it always small?
It's always small for. I mean, first you can get it from the computation. You know, you take two black holes, you compute at which moment they merge, and then what happens, roughly speaking, is V over C is still like 1/4, okay, and the emission power is like V over C to the 10, and then it is still small. So maybe we have been lucky from this point of view, and then the quasi-normal mode matching. What happens when you look at numerical simulations is the two black holes, when they merge, it's an extremely fast process. It's not there is a very complicated thing happening. The two black holes merge, like they become immediately one ringing black hole. This was the assumption we had made. And this assumption is fairly accurate.
Yeah, maybe you could explain that, because when I look at the simulation, you see these black holes coming together, and then all of a sudden it's like, whew, you know, it's like somebody put flash freeze on the whole thing. Why does that happen so suddenly? Do you have a that's your 10⁻3, right?
In part, the 10⁻³ is linked to the fact that they rotate slowly, let's say, okay?
Yeah.
It's a significant subfraction of the velocity of light. This is the small parameter because the emission is from the rotation, okay? Now, the fact that this is so fast, the merger, that they do that, it means there is no intermediate scale, I guess, that I'm not so sure, but maybe we were lucky, and then there is not something suddenly, a bubbling of the horizons, you know, a chaotic bubbling of the two horizons. So you have 2 point masses, and then suddenly you have one black hole, okay? Ringing black hole. You jump from 2 point masses going around, and then with a good approximation, they immediately jump to a state where this is one ringing black hole with quasi-normal excitation, and the transition between the two, I mean, in the EOB formalism, we just assume, okay, it's a sharp transition, we just match to second order, saying second derivative or third derivative or whatever, and it explains well the thing, even without any numerical relativity information, the waveform was good.
So it must be what you say. There's no intermediate scale. I'd like to.
I would like to understand better also. Okay.
Let's see. Perhaps I would like to come back to one point that Ashoke was mentioning. Ashoke, you are there? I guess so. Ashoke? Oh, maybe he left. He has another workshop going on at the same time. Then waiting for Ashoke to be back.
Yeah, I'm back.
Oh, you are there. Okay. Sorry. I was thinking about your little puzzle on the independence of the final massless momenta of the of this log, right?
Yeah.
So, and also in relation to the fact that you explained quite well that there were two terms, one survived in the classical limit and the other didn't. And there was an I difference between the two.
Yeah.
The factor of I difference. So my understanding is that the log omega that you got, the one which survives classically, is related to this how you call it, to this Coulomb phase that.
No, it's not just that actually.
No, it's
because
not just that.
Yeah. Because if it has Coulomb phase, then it will actually depend on the final state massless momentum because memory does, right?
Mm-hmm.
And the Coulomb phase multiplies the memory. So it will give a term that depends on the final state massless momentum. So it's partly coming from the Coulomb phase. And the other part is basically the fact that the final state particles are accelerating still under each other's gravitational force.
Yes. Okay.
And that gives rise to soft radiation.
Okay.
And these two effects cancel. The Coulomb phase and the radiation because of the acceleration of the final states.
I see. I see. But this term which survives classically is the one in which the sum over the external particles is limited to both initial or both final.
Yes, that's right. Yeah.
So, and you know that is precisely the term that Weinberg again discussed in his 65 paper when he discusses this divergent phase, not the true infrared divergence, but the divergent Coulomb phase. And that's also has this. So I thought there was a common origin. And then in that sense, you understand better, perhaps, that it doesn't depend very much on the details of the process. You know, for instance, on the
that I understand.
Deflection angle and so on. So I was just.
So I think the fact that it doesn't depend on the details of the process, that's because it's infrared.
Yeah.
But the fact that it doesn't depend on the final state massless particle momenta, that seems a little more surprising. I mean, that doesn't seem to have a very simple understanding.
Okay.
I would like to ask a question to Ashoke also. This is about this case where the coefficient of the 1 over u term vanishes when in the out state there is only one body, no?
One massive body.
So is this the same thing? What is the explanation for this? Is it also strange cancellation or something evident?
This is part of the same thing.
It's part of the same thing. Can you explain?
Part of the same thing. Yeah. So what I was describing is that even if you have multiple bodies, say multiple bodies in a final state and some massless radiation, the result depends on only those multiple massive bodies. And it so happens that if there is only one massive body in the final state and only one massive body in the initial state, right? In the initial state it's just one explosion, then the term just vanishes.
But you need also only one in the initial state.
No.
Yes, one in the initial
only one in the initial state?
Yes.
Okay. Now it makes more sense. Otherwise, there is an effect linked to the memory, no?
Yeah. So there's only one in the initial. Exactly.
Okay. Now I understand.
Okay. But there are more than one in the initial state. Then there can be memory, but this term can vanish still. I mean, it depends on the details because, as I said, if suppose you have more than one in the initial state and whatever is the final state, then there's a memory effect which is raised by the Coulomb phase. Right? That has one term. And then there is this additional effect, which is the radiation from the final state particles, just because they're accelerating. And these two effects cancel for the final state massless particles.
I see there is a question by Julio.
Hi, thanks. Yeah, I just wanted to go back actually to the question that Gabriele asked, because I think the paper by Toft that he was referring to was not the one where he looks at some particle infalling into a black hole. That was also revisited by Polchinski, but it's just the paper where he just calculates the iconal scattering using shock waves.
Yeah.
And this is like long distance scattering, and you don't even need to calculate it using shock waves. We know how to do this perturbatively in momentum space using Feynman rules, if you will. And I think what Gabriele was asking is that the S matrix that he gets in this other paper, he gets it as the difference between the bonding mass integrated over Scri and S plus and Scri minus. or this is the basic quantity that gives the diagonal phase, and there's a time delay, and I think when you calculate it using Feynman rules, I don't see where the ambiguity on which frame you're picking could come from. So maybe someone can comment on that.
No, I perfectly agree that this is the paper I was referring to. And by the way, just to make things precise, in doing this, I think we corrected a conceptual mistake in Toft's paper, who should have gotten a factor of too large a phase shift. If you remember, his reasoning was that you compute things in a special frame in which one of the two massless particles is very energetic and the other one is very soft. And he computed the time delay of the soft particle in the shock wave of the energetic one. He used this time delay times the energy. So there is a time shift times an energy, which gives the phase shift. But if you do the calculation in the opposite direction, then you compute the time shift of the energetic particle in the soft shock wave. Of course, you get a much smaller time delay, but since it's multiplied by a much higher energy, you get precisely again the same result. And Toft neglected that one. So when we did this calculation with Wilkowski, we discovered that there is this factor of too large an effect if you do a naive calculation. But if you add to the gravitational action the Gibbons-Hawking surface term, that precisely cancels half of the Toft calculation and reproduces the result that you can obtain with Feynman diagrams with no ambiguity. So, but anyway, this is just for the small history. Now, my question to Andy was referring to the fact of how is this non-trivial mapping of Sky minus into Sky plus non-trivial, because you get a impact parameter dependent or angular momentum dependent phase shift, which is the important thing, how that matches or is related to his conservation of the momentum aspect, you know, with antipodal identification. Okay, it looked to me roughly that there was a clash, but I don't know. So that was my question. I think
Andy, you are muted.
Who?
Andy is muted.
Oh, I don't know the answer to your question, Gabriel, but one thing is that all of these processes that you're computing are zero because they're exclusive and there will be infrared divergences. And those infrared divergences are, you know, they violate, these processes all violate the conservation laws. Yeah. And the infrared divergences are there to, you know, make quantum field theory consistent because you sum them up and you take the infrared cutoff. And so everything you're calculating is zero. Now, if you start computing, putting the dress state in, those stress states are exactly, the dressing is exactly implementing a super translation. Now, so to do the calculation full and properly with time shifts, you must include the gravitational dressing. Now, whether there was some good intuition at work there and the right answer came out anyway, you know, I don't want, people can, you know, get right answers without, I mean, of course, the whole history of quantum field theory, this thing is largely ignored and there's all kinds of right answers there. No,
I agree.
I won't be sure about what you're saying until if you want to talk about subtle time shifts, you had better be calculating things that obey the conservation laws.
Yeah. But okay, concerning your point, of course, is completely true. However, if you work at lowest order in G, Newton, you know, the effect of soft Bremsstrahlung still is controlled by a G Newton. And so we are working at leading order when there is no Bremsstrahlung. I mean, of course, Bremsstrahlung is very important to higher order, and actually.
Well, would you say what they're measuring is Bremsstrahlung?
No. What I'm saying is that there is an elastic process if you work to lowest order in G, like if you work lowest order in alpha in electromagnetism, then okay. But the truth is that G is finite or alpha is finite, and therefore you do have to add radiation in your calculation. Then you have to talk about dressed states and so on and so forth. But presumably, the properties of the scattering will be for small g or for small alpha will be the same.
Isn't the scattering also from gravitational effect? Doesn't that also have a g in it?
Yes.
Yeah, but it's tree level. I think I'm really saying that the effect is tree level. It's
this is a tree level effect. BMS is a tree level effect. It's not a loop effect.
Yeah,
BMS,
the phase shift is also.
And they had time delays all over the place.
I see, because the phase shift appears at tree level.
Yeah, it's certainly tree level.
So, but okay, my feeling is that once you have traced the states, you have a perfectly finite S matrix, and at leading order in G, the deflection angle is the one you compute by this naive approximation. It's like when you do E plus E minus into two jets, okay? It is true that you never produce two quarks, right? In the actual experiments, there are always gluons floating around, but if you do an inclusive enough cross-section, then the lowest order calculation gives the right result.
Just another comment, which I think it seems that this time delay, it's a kind of a subtle effect, but if the phase shift is 0, there's no deflection angle either.
Right. If the phase shift...
And that we believe that whenever when you take all subtle soft effects into account, gravitational interacting particles still deflect when...
Yes.
So how does that square?
This is clearly a subtle problem. I mean, Tuf got it wrong. You're telling me, and now there's some other. So I don't know. I can't. I haven't been through it, but you could solve the problem. Einstein said it all a century ago. You solve the constraint equations, and what you're doing is not solving the constraint equations. Now, whether it's somehow the extra terms you get by enforcing the constraint equations, which will produce some time shifts, I'm not sure. And Tuf found it corrected what he did 20 years ago, but then he corrected it again, and now you're saying it's still not right. So
no. I think
his result is right. I think he got it with the wrong reasoning, but
we got it right, but for the
we all agree on the leading iconal. Otherwise,
I see.
Our workshop.
It's probably. I'd like to understand it. I'm actually thinking about trying to understand.
Because we know what is the deflection is, right? You believe in Einstein's deflection formula for light.
Okay, so there's another example, the Shapiro time delay. People argued about that for 5 years. People didn't even believe him.
Yeah, people did.
so these things can be very subtle.
These two are different derivatives of the same object, which is the diagonal phase. So if you ask how it changes with the energy, you learn about time delay. If you ask how it changes with angular momentum, you learn about the angle. And I guess the question is whether, like, identify this antipole identification tells you that this case has to be trivial. Then there won't only be a time delay, but there will also not be a deflection angle. And that's what's confusing.
Naively, I think what Andy is saying is not that, I hope.
No.
It's subtle that.
I agree. Yeah, it's where is the subtlety? That's the question.
Yeah, where is the subtlety? That's the question.
Well, I don't know that there is one. Maybe it's all completely.
So yeah.
Maybe it's all. Maybe.
So I guess our initial state has a certain boundary mass aspect, a certain angular momentum aspect, and the final state
has a different one.
Has a different one, I would say.
That don't antipodally match.
Not completely. Certainly, to a first approximation, they antipodally match. Not
if there's any there's some deflection, right?
But there is deflection. So
yeah, then they won't.
The deflection is small.
If you just solve the constraints without using any radiation, you'll find a bonding mass aspect which has a delta function support at different points. It's you have your incoming particles, you solve the constraint equations, you don't add any radiation, that will lead to a bonding mass aspect with delta function support at 2 points on scry minus plus. And if there's a deflection angle, they will be at different points on scry plus minus.
Right.
And that needs to be corrected by adding soft stuff.
You think that this will?
That's what happens. The radiation that is produced in that process, that is the soft theorem. The radiation produced in that process you will always produce radiation, and the radiation produced in that process will erase the things on. If you leave your in-state unchanged, it will erase those 2 points of bonding mass aspect the corresponding to the angle of the outgoing particles and pull it over to exactly align with.
Yeah, this is the puzzle. We have to understand this subtlety. So, I mean, what you're saying.
That has to happen.
It has to happen.
Even it has to happen, it does happen.
Even if the radiation carries no energy or very little energy. Because my particles,
right? It won't change to leading order the total bonding mass, but it will change how it's the mass aspect is distributed over the sphere, and that's exactly what it will do. It will erase the ones that are there, and it will move them to somewhere else. So that doesn't seem like a small effect.
No.
And I would like to understand how that happens and how it affects the phase shift. And when I read those earlier papers, I'm like, well, how are they fixing their Bondi frame on scry plus? I don't understand this. And how are the constraints being obeyed?
But then you should find a way to tell me, in your point of view, whether two energetic massless particles which meet at a certain impact parameter do or do not deflect.
Oh, they'll deflect.
They will deflect.
Yeah,
so
but computing the time delay, they will deflect, but computing the time at which they come out will be a subtle problem. And you'll have to have your super translation frame exactly right to get that.
Yeah.
Okay. And that seems to be the.
But as Julio was saying, it's not so much the absolute time delay, is the way the time delay depends on the impact parameter that matters. Because then you take the derivative with respect to the impact parameter, and that will give you the deflection.
Right.
So, but we shouldn't, take all the discussion. I see two hands raised. I think Biswat he was first.
Okay, yeah. So I have two questions to Andy. One is like you just mentioned that like to make sense of like gravitational S matrix in 4 dimensions, you have to use Dress state, right? And like this is possibly what one considered as physical S matrices to make IR finite. But like using this Dress state S matrix, if we compute say single photon emission scattering process, one can see that the leading soft graviton process, then one can show that the leading soft graviton theorem is vanishing, like it vanishes. But we know that physically it has a consequence that like we know gravitational memory will be there. So I just want to understand which one is physical. Like if you consider a S matrix defined physical, which has no leading soft theorem, or like the gravitational memory which you know that one can measure that is physical. So this is one of the question.
Well, so yeah. So really, I'm not sure exactly what I said, but it's more that you have to talk about Dress states. So you don't. So Fadeev and Kulish and Chung and Kibble and all those people talked about, you know, surrounding incoming particles by clouds of soft radiation. But you know, in any real experiment, you know, at the LHC, we don't tune the incoming protons, you know, to be surrounded by clouds of you know, electromagnetic and gravitational radiation to cancel their BMS charges and their electromagnetic analogs. And certainly at LIGO, nobody surrounded those incoming black holes with dressed radiation. You know, I think that when you look at how the constraint equations for the physically realistic situation were solved in the incoming data, you had the black holes and then you had Coulomb fields coming from them, not gases of radiation to not clouds of radiation to satisfy the constraint. So, but what happens is that the dressing, the would-be dressing, goes to the out state. So outgoing, so if you scatter an E plus and if you scatter what Gabriella was talking about, the pseudo-electromagnetic, you scatter E plus and E minus, there's you know, a beam of photons that go out with the E plus and E minus, but there's also a kind of shadow beam of the incoming electron and of soft radiation that hits scry minus at the antipodal point from where the incoming electron positron came out. Now you could add a bunch of soft radiation, which would amount to dressing the initial state, and then you would only have dressed particles coming in and out. That's what Fadeev and Kulish, Chung, and Kibble talked about. And now, so in the calculation of the memory effect in the Thorne-Bruginski formula, they do something different than what Fadeev and Kulish and Chung and Kibble were doing. They don't dress any incoming states, which is the physically reasonable situations. And so, so to talk about the memory, you have to, you know, the soft photon theorem is sort of, tells you about the difference between, and you're actually asking a question. It's an important question, and it's one whose answer I'm not very clear about, but it involves in part the following. The soft photon theorem and the thing that you get from the asymptotic symmetry and the meshing is the difference between tells you a relationship between where you have the difference between an outgoing soft photon and an incoming soft photon. And here in the memory effect, you're just looking at half of that.
So like we can also consider a scattering process where there is no incoming photons, say electron-electron scattering, and like no, we know that like there will be lots of photon, and like then the, like if we don't consider Drake state, unitarity relations and other stuffs are fine. But like if we consider Drake state, then like external photon emission like from tree level diagrams will vanish because there will be cancellation from the Drake state and the extra like outgoing electron. And like but if we consider Drake state, then like the usual unitarity relation will not be hold because like you are not considering in the out state any photons unless you put a cutoff, obviously, like for the dressing.
Yeah.
So yeah, so this is a puzzle, like yeah, I never understood quite well how the dressing works.
Okay, let's move to another question. Enrico, I think.
Yeah, it's a pretty similar question. So, I mean, I still don't fully understand this like antipodal matching. Like if I think of LHC, I scatter, let's say, well, proton, and I get a two-jet event. Like, I mean, that clearly is not antipodally matched, right? Because like I have protons coming in on the C-axis, and then they have like in general, like some large scattering angle, and I can detect two jets, and like I can measure the energy correlation function at LHC, and the energy is definitely not antipodally matched to like from the incoming.
Oh, it is. It is. So first of all, let me say
sorry, but the in state there is no PT, right? Let's say the proton come along the C-axis. There's no PT, and then the coming two jets, they have non-zero PT. So like that would be non-antipodally. They would go different places in the.
So the antipodally matching is not at scri plus and scri minus. It's between scri plus minus, the bottom of scri minus, of scri plus, and scri minus plus, which is the top of scri minus.
Oh, okay.
Now it's not, you're not matching. Okay, so now, I mean, I guess, you know, people knew this 100 years ago. Maybe Maxwell probably knew. I don't know whether, maybe Maxwell didn't know it, but certainly. So if you take just a point charge, obviously, and this isn't even right, as you say, you were talking about sort of just a field theory example. If you take a point charge, stationary point charge, the electric field, it's scri plus minus, it's just 1 over r, it points in the radial direction, we put it at the origin. Obviously both antipodally and non-antipodally matched since it's spherically symmetric. But now you just boost it. And if you just boost it, you find that the value of the electric field, its spatial infinity, is not well defined. It depends on how you take the limit to spatial infinity. And if you go up to scri plus, if you go at fixed retarded time and you go up to scri plus and then down to the bottom of scri plus, you don't get the same answer if you go to scri minus and then up to the top of scri minus. It's antipodally matched. So it's a very elementary property of the relativistic propagators, and it's true of the retarded propagator, it's true of the advanced propagator, and it's true of the Feynman propagator. So the fields are antipodally matched. Now, as far as energy, the statement about energy at every angle being conserved, that's of course only true when you include gravity. The antipodal matching, it's only true when you include gravity. And when you include gravity, the Bondi, if we define the energy at each angle by the Bondi mass aspect, and we look at the time derivative of that, we see that that includes a linear term in the Bondi news, which is a total derivative and therefore integrates to 0, so isn't talked about that much. But if we include that linear term in the Bondi, total derivative term from the Bondi news. Indeed, you will find that the total energy coming in through any angle on scry minus is equal to the total energy going out any angle on scry plus. Same thing is true for
so sorry, are you saying if I had a 3-chat event at the LHC and I put a gravitational detector like opposite to one of the jets, I would measure gravitational energy?
Yes.
Radiated in that direction?
Yes, that's the soft theorem. And it's a total derivative term. It can be positive or negative. It will integrate to 0. And that is exactly the kind of effect that will move Gabriella's, it's exactly that term that will take this delta function in the Bondi mass and move it so that the antipodal matching is obeyed.
Lots to think about. There was another hand, but it was lowered.
May I make just a small historical remark, because
you're muted, Thibault.
Muted.
Thank you. I wanted to make just, thank you.
But we missed it because you muted yourself.
I'm saying it again. I just wanted to make a historical remark. Many people attribute, the discovery of memory to Deldovich and somebody else. This was first mentioned by Gibbons and Hawking several years before, in 1971. In the first paper of Gibbons and Hawking on gravitational radiation, they noticed in passing that there are qualitative differences between the gravitational wave signals, depending whether the initial state is 2 bodies or 1 body, if the final state is 1 body, and things. Just as a historical remark, because I know that Gary does not like, he mentioned, he's aware that people never mentions his work with Stephen, where they first mentioned that there were qualitative differences in gravitational wave signals. And this was linked to memory in a half implicit way, half explicit. It's the paper in which, by the way, they wrote a paper about the detection of gravitational waves, and then they put up a proposal to the English funding agencies to make a detector. Gary and Stephen, a detector at the MTP. And they are grateful that they were not funded. Otherwise, they would have to work on the detection of gravitational waves instead of going on with theoretical issues. Okay.
Nice story. Okay, I see that it's pretty late.
Yes.
I had some remarks concerning actually radiation reaction, Thibault's paper, the paper that Russo was talking
Please
about.
make a brief summary of
Do
your
you want? Because I'm also quite happy to do it some other time.
No, let's start.
I will give you a very
just
a hint. So, but that just for people who maybe were not at Russo's talk and so on. So there is this question of radiation reaction and its correction, say, to the deflection angle at 3 p.m. at order G cube. And well, there was an initial calculation in n equal 8 supergravity that picked up this radiation reaction by Carlo, Paolo, myself, Rodolfo. And then Thibault came up with a very nice shortcut to compute this radiation reaction using a linear response formula due to Bini, Donato Bini and himself, and got in a few pages,
few lines even.
Which turns out to be correct because it was later substantiated by the full calculation, the full deflection angle, including conservative and radiation reaction. Then after the Damour's paper, our group published another paper in which, without using in no way angular momentum, we computed by an unexpected, perhaps, use of soft theorems, the same radiation reaction. And we also got the same result as Thibault. And now I think everybody believes that this is the correct result. Now, why am I raising this? Not to advertise my paper, but because I think it's connected to this BMS stuff in the following sense. Thibault uses a loss of angular momentum, which is surprisingly large in the sense that it's an order G less, so higher, than the loss of energy. And if you look at how that comes about, it comes about because the initial shear, please Thibault correct me, but the initial shear of his metric in boundary coordinates is non-vanishing. Now, and this initial shear is over the G Newton. Now, if you remove that initial shear by a super translation, which you can do, and with Wilkowicki we have worked out exactly how to do it, even for an arbitrary number of initial particles, then the shear itself will be over the G square because will be the integral of the derivative of the shear. Okay, the news everybody agrees is over the G square, but the initial shear can be over the G. But if the initial shear is zero, then the shear at any time will be given by the integral of its derivative from minus infinity to any given u, and will be over the G square. So our suspicion is that the angular momentum that Thibault is talking about, whose loss is very high, okay, is over the G square instead of G cube, contains some super momentum in it relative to the angular momentum, say, the standard angular momentum which you would define in a shear-free boundary frame. So why am I mentioning this is because, okay, the fact that Thibault's angular momentum, which is presumably the correct one to use the Bini-Damour formula, and I think we have some understanding of why it is like that, is related to the usual angular momentum by super translation. Since this super translation, as Andy has explained to us, is very much related to soft theorems, or perhaps I forgot to say that the way we derived the radiation reaction was entirely based on a soft theorem. So, okay, I can smell an interesting connection between radiation reaction, boundary frames, soft theorems, and why our calculation and Thibault's, who use completely different things, lead precisely to the same result. But it's still, you know, being worked out. And as I said, if there is time in one of the future discussions, I have even prepared a few slides to show, just to explain better what I have said in words. So perhaps there is an interesting application of BMS to radiation reaction.
Yes, indeed, because actually in my calculation, not only the effect depends on the proportional to the initial shear, but it is the shear multiplied by the memory.
Exactly.
Which
okay.
is the,
exactly. Yes.
the difference between two shears. the difference between the outgoing shear and the
There
ingoing.
are very nice
Oh.
implicit connection between memory, soft
Yes.
theorems, radiation reaction computed your way, radiation reaction computed our way, which agree with brute force calculation of the same thing. So everything must be correct.
Yes.
The question is how to play with all these things. And
yes. This is why our questions to Andy were not at all intended, in a negative or you say not believing way, but on the contrary, on a positive. We want to understand better whether super translation, I mean, the full BMS could give us more information on these things.
So, and this is an example what I was mentioning. Okay, well, that's all from my side. If there is no other question, it's 6 p.m. here.
Yes, we stop.
Okay, so we thank our three animators and see you all tomorrow, I hope.
Okay, thanks.
Okay.
Hey. Bye-bye.